So in the last session, we have discussed on UVM blocking assignments and non-blocking, blocking and non-blocking. We didn't discuss till sequential execution statements, parallel execution statements, and procedural assignment statements. All these things we have discussed, right? Uh, and also have shared some online test for Verilog HDL till whatever we have completed the topics on data types, operators, blocking, non-blocking assignments, simple test benches. Have you attempted that test, everyone?
No, ma'am.
I didn't. No, Prashanti, I didn't check actually. Sorry.
I did some, ma'am.
Okay. Okay. So how much you got?
No, actually, I'm in the middle, ma'am. I not submitted.
Okay. Okay. Fine. Okay, let me revise all the topics. Then today we will write the programs for remaining combinational logic circuits. Okay, for demultiplexers, decoders, encoders, priority encoders, and comparators or some uh, multipliers. Like that, we can write the program, and I will share you the problem statements. So next, you need to write your own programs for the problem statements. Okay. So today almost we will complete all the combinational logic circuits. Okay. So any other doubts? Can you tell me what is the difference between initial block and always block? What are the rules we need to follow while writing behavioral modeling and data flow modeling? From now onwards, everyone need to start writing the programming tool. What is the difference between procedural assignment statements and continuous assignment statements, and what are the rules we need to follow while writing the behavioral modeling and data flow modeling? Sagar, Rakshita, Lahari, Rakib, Suma.
Initial executes only one time starting of the program, and always check the sensitivity list and
Okay.
execute.
Next, another difference from another
In
anyone.
in initial, we are assigning the, I mean, equations, expressions like expressions. In always, we are using the case, I mean, conditional statements like that, if or case. But in this, I didn't get the how. I mean, for loop. Can we use the for loop in the Verilog? I mean, like integer value. Can we access?
Yeah,
It
for
kind
loop.
of integer. It is not accessing actually. I checked, but
Hmm.
any other data type we need to use?
In Verilog HDL, for loop is not synthesizable. In
Yes,
test bench,
yes,
we
yeah,
can use for loop,
yeah.
but
Test
the
bench I
design.
updated, but in Verilog I didn't get that. Is there any
In
way to
design,
access the integer value in text
yeah,
bench?
let me
Sorry,
explain.
Verilog.
In design, we cannot access the for loop. It is not synthesizable. In test bench, we
Okay,
can write the for loop for the simulation. But in design also, we can use the for loop whenever we use generate block. In Verilog
okay,
HDL, we have generate block genware. So in for loop, we create int I or something, right?
mm,
That
yes,
I variable we need to create as a genware. So whenever we
okay,
create as a genware, we can synthesize that for loop.
okay, okay.
Yeah. So once
Yeah, thank you.
combinational sequential logic circuits are completed, then we will discuss those topics.
Okay, okay, fine, sure. Thank you.
Yeah. What about remaining? Any other difference? Difference between initial block and always block. What are the rules? Rakib, Rakshita, Lahari. Rakshita, have you gone through those 3 videos I shared, right?
I have just completed 2 videos, ma'am.
Okay. So did you understood what are the different data types in Verilog?
Ma'am, I didn't come for Verilog, just I watched digital circuits.
Okay. So in digital logic circuits, what is the difference between 1's complement and 2's complement?
Second.
Why do we
One's
use 2's
complement.
complement? Hmm. Yeah, tell.
One's complement invert all the bits, ma'am.
1's complement?
Invert all the bits.
In that all the bits are.
Yeah, ma'am.
That means? How do we do 1's complement? Hmm?
Ma'am, 1 minute. I have taken notes.
Okay. Rakib, Lahari, what is the difference between procedural and continuous assignment statements? Sumalata, can you answer the difference for sequential execution statements and also for parallel execution statements?
For sequential execution statements is one after another. I mean, first statement completes, then next, then after second statement. In, in continuous, all the statements completes, then assign the values to the LHS output.
Okay, so what are the blocks for sequential execution and parallel execution block? In which block we write the program? In which block we write the program? Sagar?
What, like which block?
What are the sequential execution blocks and parallel execution blocks in Verilog? Whatever we are using within the procedural assignment statements.
For parallel, we can use fork
Fork join.
join as the block.
Okay. For sequential?
For sequential, can use initial, beginning.
Always.
Begin and
Yeah.
begin blocks. Okay. In the procedural assignment statement, we have 2 types. One is a initial, one is a always. Okay, so if you are writing for combinational logic circuit, we will put always at the rate of inputs, input A, comma B, comma C, whatever, or else if there are more number of inputs, we simply put star. Okay, if you are writing for sequential logic circuit or sequential logic circuit, then we need to put as positive edge of the clock or negative edge of the clock. If you are changing the output with respect to the positive edge of the clock, we put positive clock. If you are changing the output with respect to the negative edge of the clock, then we put negative clock. Okay. So within the initial block, we write the statement. Suppose initial A equal to B, B equal to A equal to 0, B equal to 0, C equal to 0, like that. Okay. So for single statement, initially I'm making clock equal to 0. It is single statement. For single statement, we don't write any begin end blocks. Okay. Suppose if there are multiple number of statements, clock is equal to 1 and A equal to some value, B equal to some value, like that. B equal to some value, like that. There are multiple number of statements. Okay, so if there are multiple number of statements, then we need to write within the begin end. Okay, so begin end means these three statements will execute sequentially. Even you can write begin end block, or else you can write a fork join block. So instead of begin, I'm taking fork. Instead of end, I'm taking join. So these three statements will execute parallelly according to the delay. Okay, in the same way, in the always block also, if there are single statement, no need to write either begin end or fork join. Okay, if there are multiple number of statements, then we need to write begin end, statement 1, statement 2, statement 3, end. Okay, or else we can also write fork join block. Always instead of begin end, you can put fork join. Okay, so here whatever the statements are there, clock equal to 1, A equal to 9, B equal to 9, something, whatever the statements are there, there are three initial blocks within a single module. Okay, so all these three initial blocks will start execution at the same time, at zero simulation time. Okay, all always blocks start execution at zero simulation time only. Okay, but initial statements execute only one time. Only one time. Okay, so here clock is executing at zero simulation. These also executing at zero simulation, and these all are executing at zero simulation. But whatever the internal delay, suppose here there is a #5 delay, and here there is a #2 delay, and here #10 delay, and here #1 delay. Okay, so here like this, according to the delays, the statements are executing sequentially, but those delays will be added sequentially. Okay, so this clock will execute at zero. These initial blocks also execute at zero simulation time only, but 0 plus 5, 5 plus 2, 7, like that. Again 7 plus this one, next initial block 7 plus 10 something, uh, that value plus 1. Okay, like that the statements will be executed. Okay, but whereas always blocks are iteration, it runs multiple number of times until we use $finish at the simulation, at the end of the simulation. $finish means we are terminating the simulation, or we are going to stop the simulation. So at some particular time, at 100 time units. So after reaching 100 time units, the execution will be stopped. So always block execution also will be stopped. It never run after 100 time units. Okay, so this is how we can use the begin end statements and fork join statements within the initial block or always block. And rules we need to follow whenever we use the procedural assignment statement, either initial or always. LHS side variables. LHS side variables must be declared with the reg data type. RHS side variables must be declared with either wire or reg data type. Okay, whenever we use a continuous assignment statement, that means assign. Okay, so then LHS side variables must be declared with the wire data type. RHS side variables must be declared with either reg or wire data type. These are must follow rules. Okay, and other than this, what are there? Suppose if you write the behavioral modeling in design, you can use either case statement or if else. You already seen the difference between case and if else, right? If else is the serial multiplexer, case is the parallel multiplexer. Like that, we can write any number of always blocks, any number of assign blocks. Okay, so once you know these particular rules, then only you can able to write either design program or test bench program. Okay, till here everyone clear? Till here?
Ma'am, for continuous assignment, we are saying we need to declare Y for the LHS variable and register for the RHS, right? So is that affect the data flow modeling that we use assign, right?
Yes, I will show you an example.
Yeah.
Suppose you have written assign, but LHS side variable you have declared as a reg data type. It throw a error at the simulation time. You cannot use var data type. Okay, I will show that. I will
Okay.
show you
Yeah,
example.
sure.
Okay, another thing, we have another two concepts. One is a blocking assignment statement. I already told you, right? The blocking assignment, most important interview questions for freshers or experience. Blocking assignment and non-blocking assignment. Everyone try to note down. I'm telling all at one page. Okay, so blocking assignment, non-blocking assignment in the sense, whenever we use these sequential execution block, that means begin and block. Okay, so in this begin and block, the value right hand side variables we are assigning to the left hand side variables, right? That means now this one we are assigning to the clock, and here 9 is assigning to the A, and here right hand side number 9 is assigning to B. Okay, so while we are assigning these things, we can use either blocking assignment or non-blocking assignment. If I put just like this equal to, that is a blocking assignment. If I put like this less than symbol and equal to, it represents non-blocking assignment statement. For this also we have rules. We need to follow the rules in which cases we need to use the blocking or non-blocking. There are a lot of rules. In the next session, we will discuss these things. Okay, remember what is meant by blocking and non-blocking. Okay. Clear till here, everyone?
In between, voice is breaking. Can you repeat once, Prashanti?
Yeah, blocking assignment and non-blocking assignment. Okay, so here LHS side variables, the clock A, B, or the LHS side variables. Right hand side, we are assigning 1 to clock, 9 to A, 9 to B, or 10 to B. Okay, so whenever we are assigning these values to the LHS side variables, we need to follow some rules, either blocking assignment or non-blocking assignment. Okay, those things we will discuss in the coming session, next session. As of now, not required. Once the sequential statements or sequential blocks are completed, then we can discuss, but maybe in the next session we will discuss the assignments. Okay, so I'm just telling you overall idea in one page. Okay, so clear everyone till here? Hello.
Mm.
Okay, so next, decoder or demultiplexer. So how we can design a decoder or demultiplexer, 2 to 4 decoder? Have you revised the concepts of all digital logic circuit, I mean combinational circuits?
Yeah, yes, ma'am.
So how the decoder functionality will be happen?
Decoder means n is to 2 power n. Like if I give n inputs, it will output is 2 power n outputs I will get
Okay.
by
Applications
enable
of
signal.
decoder, applications of encoder and decoders.
Applications, serial communication in the data communication. Like
Okay.
enable like encoder, we can like large number of inputs we can reduce, send with the less number of information bits decoder, we can extract the less number of input and that.
Okay.
Yeah.
Okay. So I told you to design this parallel adder and subtractor. Did everyone try it?
Yes, I did, Prashanti.
For ripple carry adder, you need to add this block extra, XOR block. Did you got the output based on the mode signal? Okay, fine. So they share that link to me. I can check once again. Okay, next
Sure.
multiplexers completed. Hierarchical multiplexers also we designed, right? Did we? Or I need to explain hierarchical multiplexers.
Could you please explain how we can implement 4 by 1 mux using 2 by 1 mux, or 16 by 1 mux using 4 by 1 mux, like that?
Did you all remember the mux array model? Array model for multiplexer. This one, 19th line, this module. Assign y equal to d of select how it is executing. Did you remember? And also on the day I told you to design like this by using always block 5 always blocks for 32 by 1 multiplexer. Have you tried that?
Yes. Yeah, we did it. I did it.
Remaining? I told you to generate using 32 by 1 mux. Okay, see here, hierarchical multiplexer, how we can design 16 by 1 multiplexer using 4 by 1 multiplexer. So how, first of all, in digital logic design, how can we design in the sense 16 by 1 mux means 4 multiplexers are required at the input side. Mux 1, mux 2, mux 3, mux 4. All these are 4 by 1 mux. That means 4 number of inputs and 1 output. So here there will be 4 number of inputs. Okay, so total 16 inputs. Output side 1 multiplexer, 1 output, 16 by 1. So here also 4 by 1 multiplexer. So these 4 inputs will be given to here. And selection line. For 16 by 1 multiplexer, there will be 4 selection line. For 4 by 1 multiplexer, there will be 2 selection lines. Okay, so here we'll get 2 selection lines taking commonly. Here also 2 selection lines taking common. Here also 2 selection lines. So all selection lines are taking common to these multiplexers. And here we'll get the 2 selection lines. Okay, so S0, S1, S2, S3, like that. If selection lines are 0, 0, here this output will be getting here 0, 0, then this one is getting at the output side. If selection line is 0, 1, this one will be getting here, and here this one will be getting. Okay, based on that each selection line, based on the selection line, these multiplexers will be selected. Okay, functionality wise, once check. So how we write the program? Same as ripple carry adder. Okay, so in ripple carry adder, first we create one full adder. That full adder we take the copies, 4 copies, right? So here also we create one 4 by 1 multiplexer first. Any model, you can use a gate level model, data flow, or behavioral modeling, or array model, or concatenation operator. Okay, conditional operator, whatever. We have seen all these models. Okay, so you can design any model for 4 by 1 multiplexer, then take the copies. So copy 1, copy 2, copy 3, copy 4, copy 5. Okay, now make the connections. So what are the outputs and inputs for first multiplexer and selection line. What are the input and outputs? And here also, what are the input outputs? And here also, and last. So you need to make the connections by applying the inputs. Okay, so automatically here it will be connected. If you see here 19th line, so one 4x1 multiplexer is created. Okay, by using this mux 4x1, we have created the copies in 10th line, 11th, 12th, 13th, 14th. Okay, 4 copies. And then here we are making the connections. So here D is the input. D is the input means for these multiplexers D0 to D3. So here D0 to D3, total 4 inputs, and here D4 to D7, and next D8 to D11, and D12 to D15. So these will be the inputs. So same we need to mention here. D3 down to 0, D7 down to 4, D11 down to 8, 15 down to 9. Okay, up to down. Okay. And then T3 down to 0 in the sense, so these are T1, T0, T1, T2, T3 wire connections. Okay, T0, T1, T2, T3 are wire connections. So that's why we declared as a wire. Okay. And next signals are selection lines S0, S1. For these S2, S3 or reverse based on the function. Variables you can put any type, but whatever the lines you are keeping here, that's important. Okay, 1 down to 0, 3 down to 2. And here T0 is the output of first multiplexer, T1 is the output, and T2 is the output, T3 is the output. All these are input to the fourth multiplexer. This is how we can make the connections of 4x1 multiplexer using 16x1. Like that 8x1 multiplexer using 2x1. 8x1 means how many 2x1 multiplexers are required? So input 8 divided by 2, so 4. So you need to take 4 2x1 multiplexer, 1, 2, 3, 4. 4 2x1 multiplexers, and here again 1 2x1 multiplexer, and here again 1 2x1 multiplexer, and here these two will be connected to another 2x1 multiplexer. And here 8 inputs. Here 2 inputs and 2 inputs, 2 and 2. So 4x1 multiplexer, there will be total 3 selection lines. Okay, 3 selection lines in the sense selection line 1 will be common to all these hierarchy, and second selection line common to this, and third selection line. Total 3 selection line. Based on these 3 selection lines, we'll get the output. Okay, so you need to create the 2x1 multiplexer first. By using this 2x1, you need to make the copies 1, 2, 3, 4, 5, 6, 7. Total 7 2x1 multiplexers you need to take, and you need to put the input values. Suppose D0, D1 or the inputs to first multiplexer, D2, D3 or the inputs, D4, D5, D6, D7. Like that here wire connections T0, T1, T2, T3, and here T4, T5 or the wire connections. Like that you need to connect in the programming same way. Okay. Here test bench. 16-bit input, then what is the output? Simple test bench. Before test benches, I didn't say it. Okay, I'm considering this test bench here. So instead of D input, I input, I'm considering as a D. and 15 down to 0, and number of selection lines are 3 down to 0. Output will be Y. So D, comma S, comma Y. And what is the name of multiplexer? We are writing the test bench for top level 16 by 1 multiplexer. So DUT mentioned that 16 by 1 multiplexer. Initial begin. Here also input, selection line, output. So D, comma S, comma Y. Okay. So D equal to 16-bit input is given and selection line equal to these 0, 0, whatever, 0, 1, 1, 0, 1, 1. You can write simply by using always block also. We already discussed that. Enough till here. 1, 1, 1, double 0. Okay, now run. I will show you the synthesis also. Same program I am copying. Okay, save. Run. Meanwhile, simulation. Okay, see here. What is the input? What is the selection line? Selection line is a 0, 0, 0, 0. So here 15 down to 0. 15 down to 0 means this MSB bit, this side, the last bit is 15. LSB bit is a 0. Okay. So in 0th line, D of 0, what is there? 1. So output is 1. In D of 1, input value is 0. So output is 0. In D of 2, input value is 0. So output is 0. In D of 3, input is 1. So here 1. So output is 1. And here next 0, 0, next 0, like 3 zeros and then 1 and then 0. Okay. So this is how we can write 16 by 1 multiplexer using 4 by 1 hierarchical multiplexer. Okay. So same structure if you want to observe. This is the same structure. We need to do the synthesis. Okay. So I want to do synthesis here. Compile, design, analysis and synthesis. Netlist viewer. Rakshita, install these tools. Okay. If you find any issue, let me know. Okay. Do you have the tool before? Any synthesis or simulation tool? No?
No, ma'am. No,
Okay.
ma'am.
Okay, then install this, or else if you are, whenever you are installing, let me know. Okay,
Okay, ma'am.
so see here, this is what synthesized diagram for multiplexer. Okay, so we need to do compile design. After compilation, just go to analysis and synthesis, netlist viewer and RTL viewer. After RTL viewer, we'll get this type of multiplexer, 4 multiplexers and output multiplexer 4 by 1. Okay, and you can also check what is there in the internal circuit, internal diagram. So if you see here, multiplexer is getting select line input, data is input, out is the output. Okay, so here we have written the program as a assign y equal to d of select. It's a simple multiplexer. Okay, suppose for multiplexer, if you want to generate the gate level circuit diagram, then suppose here we have a multiplexer in terms of gates. Okay, here didn't mention now. So whatever the statement is there here, f is equal to s1 bar into s0 bar into d0 plus s1 bar into s0 into d1. Like these are from this, if you draw the circuit diagram, we will get the circuit diagram, more number of AND gates and one OR gate at the output side. So if you want to get the diagram for that, instead of this logic, you need to write the data flow modeling. Okay, data flow modeling, we already seen that example, right? Data flow or gate level also you can write the program. Then you will get the gate level circuit diagram here. Okay, will you try that or shall I write? Okay, here there is a gate level circuit diagram. I'm just copying this, and instead of this array model, just put the gate level diagram. Okay, so mux 2 by 1 instead of 2 by 1, mention 4 by 1. And what are the inputs? A, B, S out. A, B, S out. Instead of A, B, I'm taking as a D, 4 down to 3 down to 0. Input D, and selection lines 1 down to 0 selection line, and output is same, and wire in 1 into S bar. So what is the circuit diagram for 4 by 1 multiplexer? So same, you need to write NOT gate, first NOT gate, S0, S1, and 4 AND gates here, and 1 OR gate. Okay, just try this. I will try now data flow modeling.
Prashanti, I did it. Can I share that link? Can you check now?
Yeah.
Can I share that link?
Yeah, you can share in the chat box here.
Can you please check?
Okay, mux 4 is to 1. Here 2 inputs are. Okay, here 2 inputs means here we will get the error because we are taking vector format here, and here 2 inputs as a scalar format. We'll get the error, but we will check.
Yeah, you can take the test bench also.
Yeah, test bench will not synthesize here. We need to use only design. Oh, compilation is successful. Okay. Internal diagram is correct. We need to make the connections properly. Okay, so internal diagram is getting properly. Why the connections are missing in the sense, so if you see here, D is a vector format, and here we are considering 3 down to 0 here. This D and whatever the input is there, these two need to match properly. That to 4/1 input means 4 inputs will be there. 4 inputs will be there, right? Why? Okay, data is 3 down. Okay. Instead of this, I'm taking data in as a selection line and out as a output. So here in will be the two selection lines, input 1 down to 0, inner, data outer. So instead of this in 1, I'm taking as a 0 and in 2 as a 1, and here also same.
At first line, I need to take as in second one also 0, right? I mean 0, 0, 0, 1. Like that.
Because vector we are taking 1 down to 0, right? That's why 0, 1.
Okay.
And still any changes, that's it. So these port lists need to be same, match this data in out and here DSY. So then we will get proper output. Compilation means if compilation is correct means we don't know whether functionality is correct or wrong. Compilation means it check only syntax errors, if any semicolon is missing or any variable is not declared, those things only it will be checking. Okay, before also we got compilation free 100% successful, and even we got the output synthesizer diagram also, but connections are missing there. Okay, if you do the simulation to that program, you won't get the proper value. There will be a functionality error. Okay, so in that case, we need to check properly all the connections. So we will see whether we get the output or not now. Now we are getting perfect output. Okay, 4 multiplexers, 1 output. In each multiplexer, we have written in a gate level modeling. Okay. So this is what 4/1 multiplexer using 16/1 multiplexer using 4/1. Clear everyone? Any doubts still here? Next, a demultiplexer. How do we write the demultiplexer? Same as a multiplexer. In gate level, behavioral modeling. Every code I won't explain here. You need to try yourself. I'm explaining everything line to line, but if you try yourself, that would be good. So demultiplexer, if you see, will get two output expressions, right? So after multiplexer, there is a demultiplexer. Here, D0 is equal to S0 bar into input. D1 is equal to S0 into input. So how we need to write in data flow modeling? Assign D0 equal to this expression, assign D1 equal to this expression. or else we can write always at the rate of star selection line. Okay, case selection line. In that, if selection line is at 0, then what is the output? If selection line is 1, then what is the output? So we need to write like that. Or else here we have written in a data flow modeling using the output expression. Okay, so OP1 is an output 1 and OP2 output 2. So here we'll have multiple number of outputs. If it is 8 by 1 multiply 8 by 1 1 by 8 demultiplexer, then 8 number of outputs will be there. 1 by 32 demultiplexer, then one input 32 output. So 32 number of assigned statements will be getting here. Okay, so how you simplify in an array model? In multiplexer we have written all type of multiplexers in a single line array model. In demultiplexer, how you will use this same program, but little modifications. Just try with that. Okay, so here this one only this. If you do synthesis for this demultiplexer, I'm just copying this program and doing synthesis. So compilation is completed, compilation is successful, and then RTL viewer. So demultiplexer, one input, two outputs, OP1, OP2. Okay, like that, whatever the size you are considering, you can write the type of demultiplexer. Suppose here 1 to 4 demultiplexer. 1 to 4 demultiplexer means D0, D1, D2, D3. So S0, S1 or 2 selection lines you need to mention and write same program. Assign D0 equal to S1 bar into S0 bar into inner. Assign D2 equal to that expression. Assign D1 equal to, assign D3 equal to. Okay, same. Like that behavioral modeling. I will write the behavioral modeling also. Before that, if you see here, hierarchical demultiplexer. Hierarchical demultiplexer 1 by 8 demultiplexer means how we can write 1 by 8 demultiplexer using 1 by 2 demultiplexer. Same like this same as a multiplexer, but 8 by 2 means 4, but at the output connection we need to make 1, 2, 3, 4 outputs. So each 1 by 2 multiplexer. 1 by 2 means 2 outputs. Here also 2 outputs, and here 2 outputs, 2 outputs. 1 input, and here 1 2 by 1 multiplexer, again 1 input, and here 1 2 by 1 multiplexer, again 1 input, and here at the input side 1 2 by 1 multiplexer, 1 input. Okay, so for 1 by 8 demultiplexer we have 3 selection line. 1 selection line is for here, just reverse of multiplexer. Okay, now you need to write the 1 copy of 2 by 1 multiplexer. By using this 1 2 by 1 multiplexer, you need to take these many copies. Copy 1, copy 2, 3, 4, 5, 6, 7 copies and make the connections. This is how. Okay. Dmux 1 by 2 and 8 copies here. M1 to M7. Okay. So you can do synthesis. Understanding, everyone? Have any doubts? Please let me know if you have any doubts.
No, ma'am.
We need to change the name here to Dmux 1 into 2. whatever the name we are taking here for modules here. Okay. And this one top level we need to mention as a file name, Verilog1, because file name is Verilog1 here. These are just a basic blocks, but sometimes we'll be having problem statements. So from problem statements, how we need to write the program. Already I have shared assignment 1, mostly problem statements. Okay. So I will share you assignment 2 also, but you need to complete that online test first and then assignment 1. Then I will share assignment 2 in Verilog. Okay. See, hierarchical demultiplexer. In each demultiplexer, we have written using this program. Mostly data flow modeling, gate level modeling, we will get in a gates only. Okay. So first 1/2 demultiplexer and then internal. You can check for all. And here. Okay. So this is what 1/8 demultiplexer. Clear everyone? How to write the program? Everyone understood?
Yes, ma'am.
How can you design a demultiplexer using a decoder or a decoder using demultiplexer, vice versa? How can we implement? Suppose 2/1 1/2 demultiplexer. 1/2 demultiplexer means 1 input, 2 selection lines, 2 outputs, 1 selection line. For decoder, 2 to 4 decoder. 2 to 4 decoder in the sense 2 inputs, two inputs, 4 outputs, and enable signal. And here I am considering as a 1/4 demultiplexers. So 4 outputs and 2 selection lines here. So what is the difference between these two? One by two demux, 2 to 4 decoder. In demux, instead of input, we'll have enable signal in decoder. Okay, input is what? If selection line is 0 0, here this input 1 will be sent to the 0th line here. If selection line is 0 1, then to this line. If selection line is 1 0, then to this line. If selection line is 1 1, then to this line. If you draw the truth table, you will be getting output D0. It will be highlighted first, enable, then like this, then like this, then like this. Same decoder also. If enable is high, output will be getting. If enable is 0, output will be memory state. Okay, off. The circuit will be off. So here 0 0. 0 0 means what? First line will be activated. So 1 0 1. So next line will be activated. 1 0. Third line will be activated. 1 1. 1 1. So fourth line will be activated. Is there any difference between both? Huh? Mostly similar, right? Hello.
Yes, ma'am.
So how can we write the program for decoder? Here we have written in a gate level modeling. Not only gate level modeling, logically, simple logic. How we can write? Hmm? Suppose draw the truth table for decoder. Truth table will be like input 1, input 0, 2 inputs, and next enable signal. Mostly enable signal will be high, and output. Output 3 down to 0, 4 outputs, right? So output 3 down to 0, 2, 1, and 0. Okay, so if input is 0, 0, then output 0 will be high. If input is 0, 1, output 0 will be high. High. Output 1 will be 1, 0 means output 2 will be high. 1, 1 means output 3 will be high. So if you observe here how it is looking like, it's a left shift operator, right? Suppose if you write reverse 3 down 0 up to 3, then also shifting operation 1, 1, 1, 1. So without writing in a traditional way using gate level modeling or data flow modeling or behavioral modeling, we can directly put a simple shift operator. Instead of all these program, we can directly put the shifter, right? So instead of this, I'm writing a program. You can use this all. First of all, I will show with this using a circuit diagram. Okay, draw the circuit diagram for digital logic design. Go to the digital logic PPT and write the circuit diagram for decoder. See F0, F1, F2, F3, 4 output statements are getting. So circuit diagram, if you draw, you will be getting like this. This is also decoder. Okay, so like this, you will be getting the circuit diagram. This decoder is for 4 by 16 decoder. See how much big in size. If you write the gate level modeling, it will give very complex. This is just for 2 by 4 decoder, so very simple. But if you go with the 4 by 16, it's very complex. Okay, so without writing this much of complex, I just use the shift operator. Same, it will be also same output. Run, first run of this traditional block. See here how the input is 0, 0, then output this 0 is activated, input 0, 1, then output this 1 is activated, input 1, 0, then here 1 is activated, 1, 1, then here 1 is activated by using traditional model, gate level modeling. Okay, instead of logically, if you write logically, a decoder like module decoder, what are the inputs? Like input, enable signal, output. Declare the inputs. What is the size of input? Suppose 2 down to 2 input, right? 1 down to 0. and input enable signal. And what is the size of output? Output reg. I'm using the always block here. Before you have someone asked, right, what happens if we use if we don't use reg whenever we write always or whenever we write assign. So I will show you that thing now. Okay. So here always if block, if enable is high, then output is equal to 4-bit binary. Output is 0 0. I want to left shift off input. Okay. Else out is default value 0. Okay. End module. So by using just a simple shift operator, I'm just shifting left. So here whatever the value is there, I'm just using the left shift operator and writing the program. Okay. So test bench, write the test bench for this.
Ma'am, I think input we need to provide variable.
Input?
We need to give in as the variable, the 6th line.
Okay. So test bench, name of the test bench. So whatever here we declared same, you can write here. But inputs must be declared as a rich data type. You already know why. And here also. Why do we write? Can you tell me?
This is procedural assignment statements.
Okay. So inside the procedural assignment statements, we are writing the program. We are using those variables. That's why those variables must be declared with a rich data type. So input equal to B, enable equal to now enable is high default. Enable will be high and input will be binary data 2-bit 0 0 initially, and then in is equal to 2-bit binary 0 1 1 0 1 1. 0 1 1 0 1 1. As we written always block in the design, we need to use the $finish at 100 time units, or else it will keep on running until it stops execution automatically. Okay, 100 at 100 time unit $finish. Simple test bench. Now run. So these are the logics we need to know for any basic codes. See, this output is same and this output is also same. Okay, but if you write a same 224 decoder for 4/16, extra 16 number of lines you need to write. Okay, here same decoder logic, even if I write for 16 also same logic. Okay, I just need to change the input here. Input will be 4/4 inputs, output will be 16 inputs, but internal logic is same, just a single line. and at the test bed side we need to apply the inputs. Okay, so these are very important logics. Everyone understood till here?
Um, yes, ma'am. I have one doubt. We have used dollar finish, right? Uh, Instead of dollar finish, can we use dollar stop also? I think we can. We have dollar stop in Verilog, right?
Okay, what about remaining all? Why did they left?
No idea, ma'am.
Any network issue?
I don't know.
Sukumar means? Who is Sukumar?
Hello. Yeah, the Sukumar is mine, Prashanti. Suma.
Okay, fine.
Yeah, in between it, I mean, maybe network issue, it left, so again I rejoined.
Okay, fine. Okay. So this is how we can write the demultiplexer decoder program. Okay, you can try for 4x16 decoder or 8x32 decoder, 5x32 decoder like that. Okay. Next, 7-segment display. How can we write the program for 7-segment display or encoder? Encoder also same. For encoder, we'll have multiple number of input. Priority encoder is there here. What is the difference between normal encoder and priority encoder? What is the difference between normal? Yeah.
It selects the line based on the priority, like with the MSB and LSB. That is
Okay.
priority encode.
Okay. Okay. So normal encoder means the same as a decoder. Decoder means what the binary data will be converted into the physical data. So here the binary data input is binary 0001 1011. It is converting to the physical data based on the line it is activating. Okay. For encoder, these will be the input. Whatever the output is there here, that will be the input. Whatever the input is there here, that will be the output. Okay, just reverse the program and try once in gate level modeling or by using a shift operator. So how you can write a single line, just try. Okay, coming to the priority encoder, this is 1. If DIN is high, based on the priority, output will be 111. If D6 is high, that 6 will be decoded into the binary value 6. 5 will be encoded into the binary value 101. 4 will be encoded, converted into the binary value. Like that 3, 2, 1, all these values will be converted into binary. Here I have written in a, what is this operator? Can you tell?
Conditional or operator.
Conditional operator. So here we are writing the condition and writing the output. If condition is true, then we'll get the output. We can write in a conditional gate level modeling or that what data flow, whatever. We already seen all those examples. So this is a conditional operator. Okay. So check the how we have written the condition. Okay. And you asked whenever we use the assign, what is the output, right? Suppose here I am writing a reg for the assign and run. It throw a error. Out is equal to 101 and in is getting a okay. Okay. Here we have written only for input input 0 1 0. Okay. Here also it will take based on the priority. Here first one is a 7th bit, right? That's why it is taking priority of 7 only. Even if there are multiple number of ones, in priority encoder, it take first whatever we have written the value, that value. Okay, here 6, first written value is 6. So 2 inputs are given. You can take more number of inputs for all conditions, then you can observe the output. D in, so I'm removing the 0, 0. So next will be the 5. Run. So 5. Okay. So based on the priority, we can check. Okay, this is what we call as a priority encoder. Normal encoder also same maximum. Okay, any doubts till here? But here when we use reg, it should throw an error. But why it is not giving the error here?
Ma'am, I have a doubt. Just correct me if I'm wrong. Like whenever I write my test bench, like I have practiced a few circuits, and when I'm writing, I kept register for input and wire for output. Can we do like that for all the programs?
We can do. Right hand side, you can put either wire or reg, whatever. Left hand side, compulsory, you need to put reg only.
Okay.
Okay.
So input we can make it as register and output as wire. Okay.
Here output I'm putting as a reg and input as a wire. It should throw an error. We'll check.
Okay.
See, D in is not valid left hand side of a procedural assignment.
Okay.
And here also. Suppose if I write as a reg, then for out we'll get error. Okay, out is a right hand side variable, right? That's why we can use either reg or wire.
Reg or wire. Okay.
And here also, if we write as a reg out, okay, I'm doing synthesis in Bartas prime, so we will get the error there. We'll check it.
Ma'am, can we also synthesize in EDA playground?
Synthesis is not possible. We don't get proper diagram. Synthesis option is there. We don't get the diagram properly.
Okay.
Here we have synthesis tools all day. But those will not generate. Here we'll get the compilation successful because no error is there. But here I'm writing output reg here. But we'll see whether error is getting or not. But compulsory we should get the error. Yeah, getting. Okay. Continuous assignment error. Object out on left hand side of assignment must have a net type. Net type means either wire or W and whatever. Okay. mostly we spell as a wire, right? That's why we are telling as a wire, but actually we need to spell as a net data type, because in net data type we have three: wire, WR, W, and in register data type we have reg, time, integer, real. These things comes under register data type. So RHS side we can have either register data type or net data type, but left hand side we should have net data type. Okay. So next is a 7-segment display, and there are some codes we will see in the next session: binary to gray code converters and all. Meanwhile, practice these things. In the next session, we will see magnitude comparator, binary to gray code, 7-segment display, these things. Okay. Parity generator, parity checker. I will give you assignment, but I will explain in the coming session. Okay. Mostly Monday, maybe we have a session or not, I don't know. If we don't have the session, I will try to take on Sunday. If not possible, try to work on assignment. First, complete all the assignment. I will give you another assignment also. Okay. Then we'll have the session on Tuesday or Wednesday. Okay.
Okay, ma'am.
Yeah. Okay, then Suma, do you have any doubts? Okay, then thank you all.
Thank you.